Yes, so our next speaker is Łukasz. Łukasz Michalak. Yes,
Michalak, yes.
Michalak. Yes, I'm very sorry. Łukasz
Oh, no
Michalak,
problem.
and yes, and he is going to tell us about symplectic representation of surface mapping classes of algebraically finite type. So, Pan Łukasz, let's start.
Yes, thank you very much for the introduction. So I would like to say about the mapping class group and its symplectic representation in the specific part of the mapping class. So first of all, recall that the mapping class group of a surface or a manifold is just the group of all homeomorphisms. In this presentation, I will restrict to orientation-preserving homeomorphisms and divided, by the isotopy relation. So we can think about it as we divide this group by the homeomorphisms which are isotopic to the identity. And recall the classical case of the torus, where the mapping class group is isomorphic to the group of all special linear matrices 2 by 2 with integral coefficients. This isomorphism is given explicitly by the map matrix or linear map induced by the map on the torus on the first homologic group. Using these matrices, we can define known Möbius transformation of the hyperbolic plane, and using this action, we can classify them into three families, which are called elliptic, parabolic, and hyperbolic transformations. They can be described explicitly in terms of invariance of the matrix or the trace of eigenvalues. And these families of H2 isometries corresponds to three classes of the mapping classes of the torus, which are called periodic, reducible, or anosoph. Periodic, it means that some power of this mapping class is the identity. So, in fact, we always can take such periodic homomorphism whose some power is exactly identity, not the isotopic to identity. Reducible, it means that we have some circles, which corresponds to one-dimensional eigenspaces preserved by the transformation. So we can cut this torus, the surface, onto some pieces onto which the mapping class or matrix still acts. And also we have anosoph case where we have some, these eigenvalues are lambda and lambda inverse. Lambda is greater than 1 in this case. And so in some direction, we stretch the circle or the eigenspace with constant lambda, and other direction with constant lambda inverse. Okay, so this is this classical setting. So in general, for surfaces of genus at least 2, the transformation on the first homologic group is symplectic transformation because it preserves the intersection form for oriented surfaces. So in terms of matrices, there is such equality satisfied for standard matrix omega, which defines symplectic form. And classical theorem of Burkhardt states that for genus at least 2, this symplectic representation is surjective. It is not isomorphism as for G equal to 1, but it's surjective. And there is analogous, and this big theorem in the mapping class group theory. It's called Nielsen-Thurston classification. We have analogous three families of mapping classes. In the shortest way, they are called again periodic, reducible, and in the case of genus at least 2, pseudo-anosoph. But such division is not unique because these periodic and reducible classes can overlap. So we can distinguish, in fact, 4 families of mapping classes: T1, which contains periodic homeomorphisms; T2, which are reducible, so we can cut the surface onto pieces, and homomorphism is non-periodic, and any piece is not pseudo-Anosov piece, so we have no pseudo-Anosov pieces. And T4 is the family of classes exactly of containing pseudo-Anosov diffeomorphisms of a surface, and T3 contains such reducible homeomorphisms whose at least one piece is pseudo-Anosov. Yeah, okay, so these first 2 classes, T1 and T2, so without pseudo-Anosov mappings in any piece, are called algebraically finite type. And this is called by Nielsen because he conjectured that these classes can be defined explicitly in algebraic terms because he showed that all these classes induces symplectic transformation, which is quasi-unipotent, and it means that the spectrum of the symplectic matrix consists only of roots of unity. Yeah, so the spectral radius is 1, and okay, we can say it in many terms. So he conjectured that these mapping classes, quasi-unipotent mapping classes, are exactly classes of algebraically finite type, so T1, T2. So after Thurston, we know that they do not have any pseudo-Anosov piece. But yeah, with Thurston, we got the construction of a pseudo-Anosov diffeomorphism of a surface for any surface of Zenus at least 2, which induces identity as a symplectic transformation on the first homologic group. Yeah, identity is clearly quasi-unipotent. So this name and this conjecture in fact is wrong, but still we use it because they have nice algebraic properties. But in fact, Darosha provided later proper characterization of these classes of algebraically finite type. They are exactly those classes which contains a Morse-made diffeomorphism. Yeah, Morse-made diffeomorphisms are Morse-made systems, are very nice classical examples of dynamical systems, very simple. From the perspective of periodic point theory and dynamics, that this dynamic is quite poor, in contrast to pseudo-Anosov maps, whose dynamics is very rich. We have many periodic point infinity, many periodic points, dense orbits, and so on. Yeah, and so there are these two words of mapping classes for a surface. This pseudo-Anosov word and this word of no pseudo-Anosov. So as we know, of the word of Morse-made diffeomorphisms. Okay, so the question is whether how we can use symplectic representation to determine whether in which class there is now given a mapping class, in which family. So whether it contains pseudo-Anosov piece or not. And there's not good in this direction because there is known fact in the mapping class group theory that if we restrict the symplectic representation to just only pseudo-Anosov homeomorphism, diffeomorphism, then this representation is still surjective. Yeah, so any symplectic matrix we can realize by pseudo-Anosov map. In fact, we can take any matrix which induce any transformation mapping class which induces a given matrix, symplectic matrix A, and then if we compose with some Thurston example of map which induces identity with some power, then we know that for some sufficiently large power, this map is pseudo-Anosov, and of course, it induces the same transformation as F. Yeah, so this is easy proof, but we need to know why this is this is true. Okay, but so it from this perspective, we would like to we can think that the symplectic representation cannot be used in this case to distinguish between classes. This is not exactly true. There are some specific very rare cases where we can use it. But our general problem we would like to investigate, this is my work with projects, with my collaboration, is whether the symplectic representation restricted to these first two families of classes, which algebraically finite type classes, which does not contain pseudo-anodes of pieces, whether this symplectic representation is surjective. We know this is onto quasi-unipotent matrices, so the intersection with symplectic matrices we are asking whether this is surjective. And if not, what is the image? And it turns out that such simple question is, up to our knowledge, not known to today. We have some conjectures, maybe I can say at the end of my presentation. But it turns out that, okay, symplectic representation cannot be used to distinguish, so representation of a given map cannot be used to distinguish in general the type of mapping classes, but if we consider all lifts of a mapping class, lifts with respect to some finite covering of a surface, and then we consider symplectic representation of this lift. So in particular, we can calculate spectral radius of induced symplectic transformation. Then it is easy exercise that if we take the mapping class of algebraically finite type, then all lifts also are quasi-unipotent. So the spectra consists only of roots of unity. So we call this this spectral radius of lifts virtual spectral radius or visual homological eigenvalues of symplectic transformation induced by some lift. So there was a big conjecture stated by Mike Mullen that if we have pseudo-Anosov map or map which has at least one pseudo-Anosov piece, then the question is whether it has a virtual spectral radius bigger than one. So in other words, can we detect by some lift of our mapping class whether it is of algebraically finite type or not. So this is the implication, and the reverse implication is easy. This is just this sentence, and this conjecture was proved quite recently by Jin Liu. Previously were some attempts, and partially was proved, for example, by Thomas Koberda, partially some insights in the direction to confirm this conjecture. So in fact, symplectic representation can distinguish between classes, but we need to use lifts with respect to finite covers of a surface, not mapping class itself. And the fact that it is detected by lifts is not surprising because the constant lambda f, which can be defined as the largest stretch factor of a pseudo-Anosov piece. So we have many pieces after reduction of a mapping class. And for those pieces which are pseudo-Anosov, we have some of these stretch factors. Analogous are for the Anosov case. And we take lambda f as the largest. So in fact, if a map is algebraically finite type, it has no pseudo-Anosov pieces, then we define that this lambda f is 1. And this lambda f, it is known by the result of Boju-Jiang that this number can be described as equal to the asymptotic Nielsen number. So if someone knows what is the Nielsen number of a map, we take some iterations of a map, Nielsen's number of this iteration, and this limit superior of the square root of n of these Nielsen numbers, and such an asymptotic Nielsen number is equal to the lambda f, and the asymptotic Nielsen number can also be in some sense described by finite coverings of a map. And by the way, this number, the logarithm of the largest stretch factor is also equal to the topological entropy of a map. So yeah, the entropy is positive, so lambda f is at least 1. And then we have some rich dynamics because entropy is positive, but lambda f is 1, so the logarithm is 0, entropy is 0, so we have this nice world of Morse-made diffeomorphisms. Okay, so this symplectic session is helpful, but still we don't know what is the, in fact, the image of algebraically finite type mapping classes. And in fact, we are motivated to answer this question by, dynamics of Morse-made diffeomorphism and in general of periodic points of mapping classes of surface. And for such pure dynamics in the case of Morse-made diffeomorphism, some behavior on periodic points we can describe using very easy invariance, which comes from the Lefschetz number of a map. Now, Lefschetz number is probably very well known. And from the sequence of Lefschetz numbers of iterations of a map, we can construct the so-called Dort coefficients. This formula is just the Möbius inversion formula for this equality. And for such a sequence of Dort coefficients of a map, we can define the support of this sequence. These are called algebraic periods. And for algebraic periods, or from Dort coefficients, we can estimate the number of periodic points. So here Pn of f is the number of periodic points of the minimal period n. So for Morse-made diffeomorphism or for other classes of nice maps, the so-called transversal maps, this number of periodic points is bounded by below from the absolute value of those coefficients. In the odd case, but in the even case, there is a similar formula which uses the periods n and n by 2. Okay, and studying Morse-made diffeomorphism and the dynamics, we provided construction, which probably I should show on the picture. This is just the rotation on some pieces. This is rotation by 4, the action of Z-mod 4 group. This is actual action of the group Z-mod 5, and we connect such pieces, and using some proper calculations, we can realize any algebraic periods and some also I skip it Dort coefficients, so which was some open problems in the theory of dynamical systems of Morse-made diffeomorphisms. But using this construction, we can provide the estimate on the biggest, the largest order of the symplectic matrix we can get as the symplectic transformation induced by a mapping class of algebraically finite type. You will recall that for periodic homomorphisms, such elements has order at most 4G plus 2, where G is the genus of the surface. Because there are some hyperbolic, with respect to some hyperbolic structure, such periodic mapping class is isometry, and this is bounded from above by 4G plus 2. So the bound is linear in G. But for T2, where we can have some pieces, we cut the surface along circles, and we have some pieces onto which a mapping class is periodic, but the symplectic transformation can have bigger order. And in fact, we showed that this order is exponential in the square root of G log G. And in fact, this is the best what we can do is because I'm finishing for a moment. If we recall what is the Landau function, this is the largest order of a element in the symmetry group. And this function has the following asymptotic behavior. So this is exponential in the square root of n log n. And if we define the largest order in the symplectic group, order of a matrix, then the Levy-Nicholas theorem, they showed that this asymptotic behavior is the same as for Landau function. So using such a nice construction, we can, for any given n, for example, for Landau function, maximal value of Landau function, so this is some partition of a number n. As we have the partition of a permutation on the cycles. We can provide a construction of a mapping class on a surface, which is of algebraically finite type, and whose symplectic representation has exactly the order equal to the Landau function. So this is this order, and in fact, this is the best what we can do. Okay, I think that I can finish in this place. So thank you. Thank you very much.